And thanks for the invitation. So this is going to be completely different than the last talk, moving on to an experimental talk. And I'll specifically speak about two new measurement techniques that we've developed this year for measuring both the qubit states and the bosonic states of our ions. So I'm, as mentioned, oh, sorry, I didn't hook this up properly. Okay, I'm from Duke at the Duke Quantum Center, and we're a relatively new quantum center, but growing very quickly. And we specifically focus experimentally on atomic qubits. So we have trapped ions and neutral atoms. And we already have, a very large group. So we have faculty shown here, both in experiment and theory. And we're already close to 60 graduate students. So growing quickly, and we're always looking for collaborators and our theory friends. So reach out to me if you want to hear more about that. Okay, so today I'll be talking about computing with trapped ions. And what we do is we have these metal structures, and we apply voltages that create electric fields that we can trap strings of single atoms like this. So this picture is of ytterbium ions. And so they're arranged in sort of this 1D chain, but we can connect any ion to any other ion in the chain. And in this digital computing picture, sorry, I'm just going to take a moment and plug this in so I can use the clicker. There we go. Okay. And we use, at Duke at least, in our labs, we use lasers to address the ions. And so if we focus down a single laser beam to each atom, then we can do arbitrary single qubit rotations. Our 2-qubit gates, our native gate is a XX interaction in any pair. So by choosing the ions, by turning on those specific lasers, we excite the motion of the chain. These are just coupled oscillator modes. And by exciting this motion, we can couple any two ions in the chain of your choosing with this XX interaction with a variable angle. And so this allows for all-to-all connectivity in this digital model. And using these two constructions, we can make a universal computation in this digital picture. We can also work in more of an analog mode, and I would say this is kind of more the historical way of operating these long ion chains. Before we had these individual beams to do the digital operations. However, now we're kind of coming full circle around back to the analog operations, but still using these individual laser beams. So what we do is we, very similarly to what I showed on the last slide, we're exciting the motion of the chain, and we're using that to create this icing XX interaction. And since we have individual tunability on each ion, we can create actually arbitrary JIJ coupling by choosing judiciously sort of which normal mode that you're talking to, and then tuning the Rabi frequency of each ion individually. And then we can also use those beams to add what looks like magnetic field terms, so we can do both transverse and longitudinal fields in this icing model. So this is really a rich sort of programmability that we have that sort of, again, came full circle from wanting to do these digital gates and having individual beams for individual qubits. But now we come around, and now we can use it to really tune these interactions that we have. So we can go beyond sort of power law interactions that were done with global beams in the past and create any JIJ that you want. And so I would say this is only really come about recently with the technology that we have, like what we have at Duke. Okay, so I've sort of mentioned these normal modes as being used sort of as a bus to interact these qubits, but we can also use them as a quantum resource as well. And I would say this is, again, something that ions more recently have come more into, because our motional modes are technically less coherent than the qubits, right? Our coherence times on our qubits are on the order of seconds, whereas on the motional modes, it's more like tens of milliseconds, which is still pretty high. And so we're sort of exploring this more. And so these normal modes of the chain are simply coherent harmonic oscillator modes, and we can use the same spin motion or qubit motion interaction to make the qubit and the bosons talk to each other. And we can do things like engineer baths, so we can do things like chemical reactions or simulations like that. And then also create like interesting bosonic states that you might want for something like bosonic quantum error correction. And this is largely done in the group of Jonathan Holm and ETH Zurich. And so this is just sort of another tool in our toolbox, which I'll talk more about today. And the other really cool thing about ions is that we can move them around on the trap, right? So we are confined to sort of a motion that is defined by the geometry of the trap rather than where the laser beams are. But it does provide this dynamic connectivity, so we can take a long chain, split it apart into smaller pieces, recombine them, and then we still have that all-to-all connectivity within a chain, that analog programmability within a single chain, but we can then choose to reconfigure those qubits and create sort of new interaction graphs in the trap itself. So this provides a certain level of adaptability that I think is sort of up and coming in terms of our capabilities. Okay, so the first measurement method I'll talk about is for qubits. So in a long chain, this is particularly challenging to do specifically site-selective qubit readout. And this work is really pioneered by my student Jerry Chen, as well as Isabella Gotting and Chris Monroe's group. And big thanks to Boris for lending us the laser for this work. All right. So the idea is we'd like to do partial measurement of this chain of ion qubits. And so one way you might do that is you could focus a laser beam onto a single ion, and it causes the ion to fluoresce. And if you can get it tightly focused onto a single atom, then maybe it will be the only one that emits. But of course, these emitted photons can also hit the neighbor, which cause an effective readout on that neighbor qubit. And then, depending how well you can actually focus this laser beam, you might directly excite the neighbor as well. And so that causes an error. So this method has been demonstrated, particularly at Waterloo. And it was actually surprisingly effective. But of course, it requires that you have this focused readout beam for each ion, in addition to those focused gate beams, right? So you're kind of adding complexity to the system. Okay, there are other ways to do this. So the two other sort of popular ways are either shuttling or using mixed species. So in the shuttling case, you can go to the extreme where you use sort of read out one ion at a time, and because we can move them around in the trap, you just move them far away so that this laser beam does not need to be so tightly focused. The photons that come out are less likely to hit any neighbors because they're so far away. But of course, this has the overhead of moving lots of ions around, which is not a very fast process. And in the chain case, we showed how you could do this by taking a long chain and splitting it in half, moving half the chain far away and measuring the other half of the qubits. So again, this has a massive overhead of having to move the ions away. All right, and then the other case, you can do mixed species. So in this example here, we have calcium and beryllium, and so their transitions, their wavelengths are largely spectrally separated, and so you can talk to one without talking to the other. However, in order to read out the state of one species on the other species, you do need to do an interspecies interaction in order to transfer the information and then read it out. And so an example of what that looks like here is from NIST. So these are very complicated pulse sequences that require extra control parameters. Not to mention with two species, you essentially need a second set of lasers. So your experiment just doubled in size. So neither of these methods are great. And so we set about to find a new way to do this in long chains. So the idea is really very simple. So we have our chain of atoms, and let's say these are our qubit transitions, whether it be in the ground state or what have you. And what we'll do is we'll send in a tightly focused high-power laser beam, which provides an AC stark shift and shifts this single atom's levels down slightly. And then we can shine in a global beam that hits all of the atoms, but it only talks to the one that was shifted in energy. So we tune this laser beam to talk to specifically this ion. And so as long as you can sort of make a large enough shift, then you can do this without any crosstalk to the neighbors. And then this single ion you can do fluorescence readout on this, and these photons are also shifted when they're emitted, and so they're less likely to excite the neighbor. Okay, so the ingredients for doing this. So we were inspired by this idea of the OMG architecture in ions, which is just the idea that we can have ground state qubits, we can have qubits in metastable manifolds, and we can have qubits that are split sort of across the two. And then if you can convert between them and sort of do qubit operations in any of these manifolds, you can effectively create sort of 3 different types of qubits in a single atom. And a lot of components of this OMG architecture have been around for some time, but this is sort of exploded recently and got us thinking about how we could do this. The next ingredient is this idea of narrow line with cooling. So this is a calcium level diagram, and in calcium they have this narrow 729 transition. And so what we want to do is read out on these 393 photons. And so we excite, what they do is they excite to the D5 halves using this narrow transition, and then pump to this short-lived P state, which emits a photon. And so this way they can collect blue photons, these 393 blue photons, without ever shining in blue light. So this could also be called background-free detection. So this is a way to do that, but of course it requires this narrow line width addressing. And the next thing, this is actually from our neutral atom friends. So the idea here is that they use tightly focused beams to stark shift particular atoms, and then they do a shelving operation, which shelves those qubits. And then they do the readout on a different level such that those qubits that had been shelved are unaffected. And so they're doing operations on the data qubits in the form of the shelving operation, and then the readout is still happening on the broad line width dipole transition. Okay, and then the last ingredient is what we've been doing at Duke for some time now, where we have these individual addressing beams where each ion has its own individually addressed laser. So in this case, it's coming from this multi-channel AOM. And these are high-power beams for doing fast Raman gates. And they're site selective, right? So we can choose which one that we turn on. So putting all of these ingredients together, we can do this site selective measurement. So this leads to sort of some conditions for doing this. So first, we need these single site addressing high power beams that will provide the stark shift. And we actually have those in our systems already, right? Our gate beams are already these high power individually focused beams. So in the case of barium, these are 532 beams. And then we can add some global beams that address the entire chain. These are somewhat easy to do. And then next, we want a closed fluorescence cycle. So we want to be able to collect many, many photons so we can do a high fidelity readout. So in the case of barium, this cycle is going to be from S1 half to D3 halves. This is a 2 micron line, and then a 650 repumper, and so we emit at 493. And so we can do many, many cycles without getting lost in any dark states. And then the last thing is that we need a narrow transition for readout. So this 2 micron transition has sub-hertz line width, for example. And so as long as we can create large stark shifts, say over 100 megahertz, then when we shift this level away from the neighbor, there's virtually no excitation left on that narrow transition, 100 megahertz away from a hertz line width transition. So these ingredients, I'm giving barium as an example because that's what I'll talk about in the experiment that we did. But these ingredients exist in other atomic species, of course. So as long as you can meet these, then you can do this method on that species. So it's not specific to barium, but that's what I'll talk about next. Okay, so in 138, the way this works, so our qubit is in the ground state here, in the minus 1/2 plus 1/2, and we're going to turn on this 532 beam, which Stark shifts the S1/2 levels down. And then the first step is to shelve the 0 state. So in barium 138, this splitting is only a few megahertz. So in hyperfine species, it would be gigahertz. So this shelving is maybe not so necessary. But in any case, in 138, we shelve up to this dark D5 halves, the 0 state. And again, this is another narrow line width transition. So as long as we're largely Stark shifted, only the atom that we select sees the 1762 light, the shelving light. The next step is to just do this readout. So we turn on this cycling transition with a 2 micron transition. And then we do a reset. And so the reset, we just, again, use this same narrow line width. Everything is still shifted, and we do sort of a standard reset of our qubit. So everything that's happening here is these are sort of bread and butter operations for barium 138. The key is just doing it, in this shifted manifold. Okay, and so we were able to do this in a small experiment just to sort of show proof of principle as ideas here. And so this is a really small Stark shift. This is only 1 megahertz Stark shift that we're able to do. We're limited by the stability of our Stark shifting beam in this experiment. It really wasn't built for this. But nonetheless, we're able to do it. And so we still have 97 or 98% readout. And this inset is showing that as we try and go to higher Stark shifts, this fidelity just really drops off. As we try to increase the intensity of that 532, we hit some technical limitations that don't let us get to higher Stark shifts in this setup. However, this shows that as we're doing, again, these sort of typical barium operations in the shifted manifold, and we can still do the readout. So the atomic physics works. And then we also show that we can do a reset. So this is in about 100 microseconds or so, and this is at a 2 megahertz Stark shift. And we're limited here essentially by the amount of power we have in that narrow beam, in the 2 micron beam. And this is easily made much faster. And then finally, we can look at the coherence of the data qubit. So I was showing sort of the readout qubit operations. We can also just check that this actually isn't affecting the nearby ions. This is a single qubit experiment just to show sort of the conditions that would happen on that neighbor. And so first we measure sort of a T2 time, and we see that even with, so the blue is the baseline, and then even with a small 12 megahertz Stark shift, we're already back at the baseline, which was bad to begin with, I'll admit. But we see no reason that this should be a limitation, because we're effectively limited by the line width and the power on the 2 micron laser, which we think can be easily improved by buying a new laser. Okay. And then we also project our sort of bit flip type errors. And so this is going to be just limited by how much Stark shift you can apply. Sort of how far away can you shift these operations from the neighbors such that they really don't see what's going on. And so this is showing the predicted infidelity as a function of the laser intensity. So on this plot, about 6 megawatts per centimeter squared gets us about 150 megahertz Stark shift, and which has been achieved before experimentally in barium. And so we can project that with a improvement in the mid-circuit measurement time, because of course this scales with the time that you have the lasers on, we can get below 10 to the minus 3 errors on the data qubit. And this is sort of the blue is a really conservative estimate, sort of using about the 2 qubit gate time, and then the red is projecting to what we think is a reasonable readout time for barium compared to sort of state-of-the-art in ytterbium. Okay, so what we'd like to do is, of course, implement this on a long chain. These experiments were all in single ions, and go to larger Stark shifts. The largest Stark shift we got to was about 10 or 12 megahertz, but we'd like to show that you can really do this with 100, 150 megahertz Stark shifts. And this will require a stable 2-micron laser. We're also working on some simulations related to the motion during this process. So, for example, this is the stark shift on the D 3/2 energy levels. And so these are increasing with laser intensity, which is anti-trapping if you consider this as like sort of a dipole force, this tightly focused beam. So we're not really sure what's going to happen as we cycle these photons and what will happen to the motion in the chain. So that's something that we're studying right now. And ultimately, we'll need to add motional reset as well. These scattered photons will presumably add some heat to the chain, and we'll need to recool. But we think based on those narrow line with cooling results from Zurich that this is totally extendable. Okay, so that's the qubit readout. So next I'll talk about reading out bosons. And so, the fancy words for this maybe bosonic quantum signal processing is the idea. And the lead student on this is my student Joseph Bryan, and then our collaborator at Duke on the theory side is Stephen Teichsworth. Okay, so quantum signal processing was a term coined in 2017 by Lo and Chuang. And the idea is just that it's optimal discrete quantum control. So you're putting together a series of pulses, and in the context of this naming of QSP, this was to map Hamiltonian evolution onto single ancilla qubit rotations. So it only uses a single ancilla qubit and just does sort of specified, optimally calculated, or sort of a numerically optimized rotations in order to faithfully sort of execute the Hamiltonian evolution. This optimal could also refer to sort of optimizing against certain error mechanisms, right? So making something robust to, say, laser intensity fluctuations. And really, this is just another way of casting these composite pulse sequences that have been done in NMR since the 90s. And one example of that that's used in ions frequently is called the SK1. And sort of to give an example, what was last year, at least anyway, the highest single qubit gate fidelity, to count all the 9s, there's 5 of them, right? So this is using an SK1 composite pulse sequence, and you can see how it sort of works in this plot here. So in this execution, they're using microwaves, and so they're actually moving the ion in order to execute the gate, like through the microwave field. What you can see is that as they move along this axis, this is the excitation probability to do this pi pulse. So when the ion is here, it should flip, and when it's here, it should do nothing. And so this SK1 effectively flattens out the regions around those two locations. So this makes it robust to positioning errors. So even if you're off by a little bit, you're still going to get a pi pulse. Okay, so this is something we sort of already do for our single qubit gates. And now what we've recently been done is extending these techniques into the bosons. And so the idea here is we have our qubit carrier transition. So in this particular result from Innsbruck, they're using calcium, so S and D. These are just the qubit levels here. So we have the carrier transition on the qubit, and then we also have this ladder of states from the bosons, right? And so these are, in this ion, these are spaced by hundreds of terahertz on the qubit, and then these are just a megahertz or so on the bosons. And then this blue sideband is this anti-Jaynes-Cummings term, where we can both excite the qubit and add a phonon. And this blue sideband can be driven no matter what number of quanta you have. However, the Rabi frequency depends on the number of motional quanta. It depends on what motional state you're in. And in particular, it depends on it like this. So this is the ratio of the blue sideband Rabi frequency to the carrier Rabi frequency. And so it depends on the motional state. And these are for different lambdicate parameters. So it is sensitive to that. You have to measure it. But the point is just that, especially these low phonon numbers, it's extremely sensitive to the number of phonons. Okay, and so what they do in this Innsbruck result is they create sort of this narrowband filter on the phonon number. So the question they're trying to answer is, I have some motional mode, it's in assuming sort of some number state, and they're asking, is it 4? Yes or no? Are there 4 phonons? And so it creates this very narrow band excitation right around 4 phonons. And so when they apply this is created using these composite pulse sequences, using the sort of the quantum signal processing idea. You apply a series of pulses now in the blue sideband, which is also talking to the motion. And by putting them together in a certain series of phases and amplitudes, you can effectively numerically optimize these. And as you increase the number of pulses that you add to this composite pulse sequence, you can increase the accuracy of this filter. And so if the bosonic mode has 4 phonons, then the ion is excited. Okay, so inspired by this, we've created a different type of filter. You can call it a bosonic low-pass filter. So the idea here is we actually start, for reasons I'll mention later, with the qubit state excited in 1. And then if the energy is above some barrier, then we flip the qubit. Whereas if the energy is less than that barrier, the n rather is less than that barrier, then we leave the qubit state as is. And so this sort of creates kind of a low-pass filter where you can keep the instances, the shots where you have low energy, and you'll be alerted to those where you're sort of above the barrier, is one way to think about it. You're sort of truncating the Hilbert space to the low n values. And so this is an example of what one of these composite pulse sequences look like, where we vary the phase over time. And this is just sort of a numerical optimization, so they look kind of funny. And we can do this for various barriers. So this is just shown for n equals 2 and n equals 3. But you can do this for up to, say, hundreds of quanta without really increasing the length of the pulse. Okay, and so we were able to verify the operation of these pulses. And so we did this by creating a number state using blue sideband pulses. So we start in the ground state and add 1 phonon at a time. And then we can apply the step pulse. So it's designed, in this case, anything above 2 should flip. In this case, anything above 3. And so the dark, the colored in points are the experiment. And then we're able to pretty much account for our error in terms of Rabi frequency fluctuations. So we're able to accurately apply this step pulse in order to measure, whether we're above or below the barrier in energy. So this is sort of a specific type of sort of bosonic measurement, and we were particularly interested in it in order to measure what are called first passage times. So there may be other uses for this, which I won't have time to get to. But just to give you one example. So if I have a harmonic oscillator, I can, for example, but you'll see there are many definitions of first passage times, I can define sort of this surviving domain as anything with energy less than this barrier. And then an absorbing domain is anything greater. And then the first passage time, which is like historically more of a classical thing. So we have our sort of classical particle in this harmonic oscillator space, and at some point it escapes this region, and you record lots of trials of this happening. And these are the first passage times, the first time that it leaves this boundary. Okay? And so then you put all these trials together, and you can construct a first passage time distribution, which is essentially the probability of first passage versus time, right? And so classically, these are used in all sorts of places. So for example, analyzing the free energy landscape and protein folding, trying to find sort of the moment that the protein folds into place. Another example is looking at noise-induced switching in these tunnel diodes, and then even something like the financial market behavior, looking at risk control and algorithmic trading, sort of, you can write that. So in this case, this barrier, the threshold is sort of some price in the stock, for example. So you can use these first passage time distributions to study these sort of processes and learn about them. So why do this instead of some sort of like average, right? So first passage times give you a shot-to-shot measurement, right? So if you're just sort of looking at average rates of things happening, you lose track of these rare events. So something that occasionally maybe it takes a really long time to escape, or occasionally you escape really quickly. And so this gives you access to that shot-to-shot information. They're also extremely sensitive to noise scaling. So whether you have different colors of noise, whether you're 1 over f, 1 over f squared, where the low frequency cutoff is, where the high frequency cutoff is, all this information is embedded into the moments of this first passage distribution. So you can learn a lot about the noise that's driving the process. We also have some ideas about sort of creating binary single quantum sensing. I won't have time to get into that. And then there's some suggested quantum advantage in this quantum walk search algorithm using first passage times. We're also interested in them because they have some interesting differences when you move from classical to quantum. So these processes have mainly been studied in the classical space, and more recently just sort of getting into quantum, right? And there are some important differences, right? So classically, you can sort of just watch the particle, and when it escapes, you record the time, right? But quantum mechanically, first you have to be able to do some sort of stroboscopic measurement, so you need some sort of weak measurement or indirect measurement such that you can keep probing without sort of being able to continuously watch, right? And then also you can have parts of your state that are above the energy barrier when you measure, and then you may or may not measure your above the energy barrier at that point. So the measurements themselves are also inducing randomness, which is not the classical case. And then finally, of course, you can have things like tunneling and superposition or entanglement that are very different. Okay, yeah. So the idea is we're going to use this step pulse, this low-pass filter that we created. We choose some energy barrier. This is a small mistake here. So in each trial, we don't cool to ground state. We do that first. And the trial starts, we involve for some time. We do this conditional measurement. And in particular, if we're above the barrier, we set it such that the ion will fluoresce when we're above the barrier, and it will be dark when we're below. So in that way, if we're dark, no photons are emitted. And then we sort of don't destroy the motional state, and we can keep going with the trial. However, if we detect the bright ion, then the trial ends because we've escaped. We record the time and then continue with the next trial. And so this sort of bosonic readout that we designed works great for this particular application. And so we study this in the case of just the additive noise that's present just from the trap. There's some sort of electric field noise, some forces that are driving the ion. And so we measure for 3 different barrier heights, and we see very good agreement with our predictions. So the solid lines here are predictions, not fits, based on independent heating rate measurements. So we see the properties that we expect. We see this exponential scaling in the long time. And so this is the first measurement of a quantum first passage time distribution that we know of. Okay, so I know that I'm out of time. I just want to briefly mention sort of our systems that are doing these things that I've been talking about. So in particular, we have several trapped ion quantum computing systems at Duke, and they're all, the ones that I mentioned here are based on trapped ions and using long chains, so we can do these kind of bosonic operations, the digital computing, the analog computing. These are all within our toolbox. And we really look at these as not just physics experiments, right? These are large engineering tasks to build these systems to these capabilities. And so we think about this at sort of every level, including the software and the compilers and all of these things. So we have folks not just in the applications, but also everything in between in computer engineering space. One of the systems that I work on is the ytterbium system. We're currently working with 11 qubits, and we have all of these features that I talked about, including the mid-circuit measurement, which has a slightly different flavor in ytterbium, but follows the same idea of using these tightly focused beams. And then I just want to finally mention, in the future, what we're working towards is going from 1 long chain towards 3 long chains in a row, so they can be independently and simultaneously operated, but then also split and recombined in order to create sort of an adaptable connectivity graph. And so we recently were awarded by NSF to finish this, the construction of this system. So it will be a 96-qubit system based on barium, and I would say ready in about a year and a half is the goal. So this is kind of what it looks like right now. It's a cryogenic system. So for the experimentalists, I'm happy to talk more about that offline. We're also building at Duke a 256-qubit quantum computing system. So this is a large, ongoing NSF-sponsored effort led by Ken Brown. Yeah, we're hiring, so if you're interested, come talk to me about that. And so finally, let me just say my thank you. So this is my group with a recent trip to the Rage Room, which highly recommend if you need to get some energy out for your grad students. Yeah, thank you to my collaborators in the funding agencies. Thank y'all.
Yeah, thanks, Crystal, for this very nice talk. So, questions?
Yes, thanks for the very cool talk. I just want to maybe clarify, so for the first passage time measurement that you showed, there are also series predictions. So is there a statement that the measurement result is indicative of some quantum feature, or like you talk about the different like nice features that this measurement could potentially reveal? Like, so is it what would, yeah, like as a series, like how should I read the measurement result?
Yeah, good question. So the specific model that we're studying with this harmonic oscillator driven with additive noise, we're actually able to like fully calculate what we would expect for that in terms of first passage time, and then we can correlate it with the classical case. So we're sort of in this particular case where we have a classical analog, and then it corresponds to what we see in the quantum case in this particular setup. However, as soon as you start changing that, like you add multiplicative noise, or maybe you switch from something noisy to something coherent driving the system, and the measurement induces the randomness, then there stop being classical analogs, and you get sort of into this quantum first passage picture. And that's something that we're still exploring, I would say. And then in terms of sort of what makes it quantum, well, we're really in this sort of ground state quantized harmonic oscillator picture. And so there's some subtle differences that happen when you only have like a few, up to maybe 2 quanta. And then you can start to say, oh, well, there's a coherent state sort of description. But I don't have time to get into all of that. But so this is definitely the first quantum first passage time measurement, in the sense that, you know, this is really happening like with a quantum harmonic oscillator, right? But I'd say that's kind of where we're going, is how can we get even more quantum?
So maybe to make the question more concrete, and
yeah,
we can also discuss offline, like, is there a statement in which, like, if you start from, let's say, a non-Gaussian state, or like, can one make that distinction, or like, even if you're staying in Gaussian state, you talk about linear drive, so even if you're using a coherent state and you do this measurement, you will be able to detect something quantum, like, is there something?
Yeah, so we actually did this experiment too, but I didn't, we haven't presented the results anywhere yet, but yeah, we've been able to like make coherent states and then do these exact sort of measurements with increasing barriers. Yeah, and you just sort of see what you would classically expect. But we haven't really gotten into the more sort of interesting cases yet, I would say. Yeah.
Thank you.
Hi. So lots of people here, I guess, are interested in mid-circuit measurements for dynamics and quantum information. So you showed some nice results on the current status, I guess, on the projection for when you might shorten the readout time, and that would lower the errors. But also, I mean, I don't know anything, but I would guess that the time in which you are collecting this readout also affects the signal in addition to the noise. So is there a fundamental limitation to how short of a time you can have for this readout, and how does that compare to the gate time?
Right, so we're mostly limited by the laser power in the 2-micron beam. So but I think based on some recent discussions with vendors, I think we'll have more than enough power. So I think then we're sort of limited by how many photons we can actually collect. So this isn't a super high NA imaging. So we do need to cycle enough photons that we can get good thresholding on the state. But it's not limited by something fundamental. These are purely like technical limitations.
So you envision having these readouts that are as fast as the gates?
Yeah. So So in the two examples I showed, so the one example was as fast as gates conservatively, and we could definitely be doing that. And then the sort of faster estimate based on all these technical considerations is about a factor of 10 faster than a 2-qubit gate.
Right. Thanks.
Mm-hmm. Oh, and sorry, the one other point maybe that's important too is in our systems, our 2-qubit gates are all serialized, right? We don't do parallel 2-qubit gates, but this readout could be totally parallel. So you just choose like however many ions you wanted to read out and do that in a parallel way.
Hi, thank you for this talk. I also maybe have some technical questions about the readout. So if I understand correctly, when you do the readout, you kind of use this, I forgot, you have a loop and you have a decay. Right. You detect that spontaneous decay photons for the readout. Is this for speed up the readout, or why you don't directly use this 2 micrometer for readout?
Oh, okay. So the narrow line width transition goes to a metastable state with a lifetime of, actually in barium, I think it's 30 seconds.
It's too long, too
yeah,
slow.
Much too slow.
Yeah. Then I was wondering, because this channel for the spontaneous decay photons itself is a broader transition, right? Then will crosstalk still happen?
Right. So you could still have that photon hit a neighbor, and it's about it is much wider, so that it's about 20 megahertz. But again, it's still shifted by 150 megahertz. So the chance that it excites is lower, and then the cross section is already very small, actually. In terms of the probability that it actually hits a neighbor. So we do include that in our error projections. But additionally, I would say this experiment at Waterloo, where they actually do tightly focused readout beams, they exceeded that projection and the fidelity. So, and nobody's really sure why. So it seems like this effect of the photons hitting the neighbor is even smaller in practice than it is in principle, and in principle we're still below 10 to the minus 3 at reasonable parameters.
Thank you.
Yeah, thanks for the question.
One quick question. At the beginning you mentioned that you can tune the Ising model, or can you do all the parameters independently, both in sign and
Yeah, exactly. Yeah, so we can do each part of this independently and arbitrarily. So the B fields and the JIJ are done in.
The trace can be both positive and negative, right? Or are you restricted to?
Yeah. So I mean, yeah. In principle, these mode participations could be negative. So I think, yeah, it's totally arbitrary.
Yeah, and I also had a question. So for the last part, when you had these 3 chains that you say you could move around, can you do this like dynamically during an experiment itself, or is it only?
Yeah, exactly. We can. Yeah. So in the same, this is sort of actually a extension of things that they do at places like Quantinuum, where they're constantly moving ions during a computation. So they move ions for every single gate, every single readout that happens. So this is sort of a subset of that, where now we only have to move to sort of recombine the chains and create new connections that we wanted. But yeah, this is something that is somewhat standard in ions.
Okay, with that, let's thank Crystal for this very nice talk. And then we have a break until 11 a.m.